Hello and welcome once again to Mathspirational. In this video we're going to be looking at applying Kruskal's algorithm to find the minimum spanning tree of a network. So before we start looking at Kruskal's algorithm, we're going to have a quick look at what a minimum spanning tree is. A minimum spanning tree is the set, or rather the subset, of all the edges within a network that connects all of the vertices with the minimum possible weight. Now, there's a number of different algorithms that allow us to do this, and Kruskal's is probably the most basic. It has only 3 steps in it. The first step is to identify the edge with the lowest weight and to draw it in, making a note of it as you do so. So I'll do that by highlighting it. So our shortest edge is going to be A to E. So let's put that in yellow and make a little note of it. A to E, and I'll include its weight because I know at the end I'm almost certainly going to have to work out the total weight of the minimum spanning tree. Okay, step 2, identify the edge with the next lowest weight and draw it in, making a note of it as you do so, so long as it does not form a cycle. A cycle would mean I'd end up with a loop connecting 3 vertices so that there's different options for getting to different vertices. If more than one edge has the same weight, which isn't going to be a problem with this network, then you just arbitrarily pick one. So, step 2, next lowest weight will be E to D. So, E to D, which is 4. Okay, step 3, repeat step 2 until all the vertices are connected. Okay, so back to step 2, identify the next lightest edge. That's going to be D to C, which is 5. Next lightest is going to be C to B, which is 6. Right, at this point I've got 2 reasons for stopping. The first is that I've connected all the vertices, and the next is that if I try to connect any more edges into the minimum spanning tree, I'll start creating cycles. That will automatically happen as soon as you've got all your vertices connected. So there we have it. We've got a minimum spanning tree which has a weight of 18. Okay. So that's a basic algorithm. Let's get applying that to an exam question. So what we have here is a question from a non-pilot use of maths paper. We have a network which shows some of the roads connecting 10 of the main attractions in Rome. The numbers on the edges represent the lengths of the roads in kilometers because it's in Europe. The city council is to connect these 10 attractions with a computer system which will display waiting times at each attraction. This is to help tourists decide in which order they should visit these attractions. The cabling for the computer system is to be laid alongside some of the existing roads. Question A, 1. Use Kruskal's algorithm to find a minimum spanning tree for the 10 attractions. Indicate the order in which you select the edges. So, first things first, let's identify the edge that has the least weight. Looking at it, that's going to be AP. So, AP, which is 0.8. Next one would be A to T, which is 0.9. The next would be T to P, which is 1.2. However, that would form a cycle, so we don't use that. So we look at the next shortest one, which is T to S, which is 1.5. Next up is P to V at 1.9. Now you'll notice that in choosing that I skipped A to S, which is 1.7. Again, I skipped it because it would form a cycle. Next choice would be P to C, which is 2. That's my next shortest. Now, next up, I should probably look at A to V. However, that's going to cause a cycle to form, so we're going to ignore that, and instead go to IO. Which is 2.5. Now you'll notice that that's not connected to the existing tree. So what I actually have at the moment is a forest. A collection of trees is called a forest. Okay, next up. What we've got? We've got VC, which is 2.8. That's going to form a cycle. Oh, we've skipped TC, but again that forms a cycle, so we need to ignore that. It looks like our next one should be CB, which is 3.7. Okay. So after that, we've got OV, which is 4, which leaves us just needing to connect F into our tree. So it's either going to have to be BF or CF. And BF is the shortest of those two. So let's put that in. BF, which is 4.3. So that's first question. Now the next one, state the minimum length of cabling needed. That comes out to 21.6 kilometers. Let's not forget our units. And finally, it says draw your minimum spanning tree. Now in the exam, the examiner isn't going to have this diagram. That's part of the question. So you're going to have to draw that separately for him. So dead quickly, what does it look like? We're going to have I to O, O to V, V to P, P to A to T, T to S, and coming down to C, across to B, and down to F. Okay. Happy days, we've got 8 marks so far. Give a reason why your solution to part A may not be the solution chosen by the City Council. It could be that one of the roads isn't appropriate, or if for some reason they don't want to dig up a road. So your answer to that would be, for that, a road may not be appropriate. Okay. Right, part C. There is already a cable connecting C to F. Ah. So that means C to F, where's C to F, is already in place. So if we've already got C, we no longer need either BT or B to F. Well, B to F is the longer of the two of those, so let's get rid of that. Okay. So if we do that, we can reduce our spanning tree by 4.3 kilometers. So that means we only need 17.4 kilometers of cable. Winner. C part 2. The council finds it cannot lay a cable connecting A to T directly. So we can't have that. So in order to connect up, make it a minimum spanning tree, we need to connect our T to S onto our tree. what are our options? We can't have A to T, so we could connect up A to S, which is 1.7, or we could connect up P to T, which is 1.2. Well, of those two, P to T is shorter, so we'd use that. It's 0.3 kilometers longer than A to T was, so P to T take away A to T is 1.2, take away 0.9, so we need an additional 0.3 kilometers. And that, ladies and gentlemen, boys and girls, is Kruskal's algorithm. Okay, I hope that was helpful. I hope you liked it. If you've got any questions, feel free to leave them in the comments, and if I see them, I'll answer them. If you liked it, feel free to like and subscribe. Thank you very much.